Hello, everyone. Today we'll go over the solution to problem 3 of the USACO February 2026 Silver Contest. And in this problem, you're given n points in the XY coordinate plane, and you're allowed to do the following operations any number of times. The first operation is you can remove 2 points, which are a distance of exactly 1 from each other. And the second operation is you can swap the y coordinates of any two different points. And you're given t test cases, and you have to determine for each test case whether it's possible to remove all n points. And here's an example of a test case with 4 points. And here's a sequence of operations you can do. So first, you can swap the y coordinates of points 1 and 3 to get points 6, 1 and 8, 10. Next, you can swap the y coordinates of points 2 and 4 to get 7, 1 and 8, 11. And after this, you can remove points 1 and 2 and points 3 and 4. So you can see points 1 and 2 are horizontally adjacent and points 3 and 4 are vertically adjacent. But regardless, they're both distance 1 from each other, which allows us to remove them. So the answer for this test case would be yes, because there is a sequence of operation which allows us to remove all 4 points. So there are a series of observations that we need to make to get to the full solution for this problem. The first observation we can make is that we can consider doing all the type 2 operations before all type 1 operations. Essentially, we'll do all the swaps first, and then we'll just remove the points. And this works because it really doesn't matter the order in which we swap and remove. And because of this, we can actually consider x and y coordinates separately. Like we can consider every permutation of the y coordinates since there is a sequence of swaps, which will get to that permutation. And we can think of it as like for each coordinate, we're just going to assign a y coordinate from the list of y coordinates. The next observation we can make is that we can think about the pairs of x coordinates and the y coordinates in the type 1 operations. So in the 2 points that we remove, what do the x coordinate and y coordinate pairs look like? We can see that there's two different types of pairs. The first is like a same pair where the coordinates are the same, and there's also an adjacent pair where the coordinates differ by 1. And we can see that these 2 points have distance exactly 1 if like either the x coordinate pair is a same pair and the y coordinates are adjacent, or the other way around. The x coordinates are adjacent and the y coordinates are the same. So we need to match these two different types of pairs with each other. And now we can make another observation. If we consider one set of coordinates only, so in this case, we'll consider only y coordinates, but this also applies to x coordinates. We need to pair them up into n divided by 2 pairs for each of the type 1 operations. And we really only care about the number of adjacent pairs versus the number of same pairs, because each adjacent pair needs to be mapped to a same pair in the opposite coordinate and vice versa. So if we let A be the number of adjacent pairs we make, that means every other pair has to be a same pair. And the goal that we need to do is to determine the set of possible values of A. And if we repeat this process for both x and y coordinates, we can determine the answer. Essentially, we can check if there's a match between the number of adjacent pairs we can make with x coordinates and the number of adjacent pairs we can make with y coordinates. And now we can ask ourselves the question, what's like the minimum or maximum value of A we can get? So what is the minimum or maximum number of adjacent pairs we can make given a list of coordinates? And something that will be helpful for us is to define f of I as the frequency of coordinate I, so the number of points with that given coordinate. Observation we can now make is that if this f of I is odd, then one of the coordinates must be in an adjacent pair. So if the number of coordinates with a certain frequency is odd, then it's impossible to pair them up into like same pairs. One of them has to be paired with I minus 1 or I plus 1. And so this leads us to a greedy algorithm to map for matching these. So we can go from the lowest to the highest coordinate. And essentially, if we come across a coordinate with an odd frequency, then we have to pair it with the coordinate above because we assume we already processed all the previous coordinates. So we've processed I minus 1 and below. And we can update this. We can update the frequencies and remove this pair to sort of reflect this. And as we're doing so, we can keep track of the number of pairs removed, and we can store in the variable pair odd, essentially, which is like the number. This is a lower bound for the number of adjacent pairs we need because of these odd frequencies. And after this process, if we still have an odd frequency left over, or if we have a negative frequency, if we're not able to pair it up, then this it's impossible to like the answer is no, it's impossible to make these pairs. Okay, so here's sort of a visualization of this project. We have sort of like a scatter plot of all the coordinates that we have. So from left to right, we have like all our different coordinates, and sort of the height of each of these bars is the number of points with that coordinate. It's the frequency. So if we go from left to right, we can see what our algorithm would do, right? So first we encountered this point where there's only one point with that coordinate. So it's an odd frequency, and therefore it has to be in an adjacent pair. So we pair it with the first coordinate of the frequency higher to it. And then after we remove this pair, we're left with the even number of remaining points. So we're good. And then we can move on to the next one. So we have a odd number here. So we pair it up with the one with the one next to it. And if we have an even number, we don't need to do anything. We can, because we could pair these up into same pairs. And similarly for this, once we kind of odd, we here. And we can also like have these chain effects where if the first column is odd and the next column is even, removing one pair will make this column become odd. And so we'll remove this pair, and now this column will have 1 point left, which means it will have to pair with the next column. And this will give us a sort of lower bound on the number of adjacent pairs we need because it's not possible to use like it's not possible to like fill these coordinates with only same pairs since we have an odd number of them. Okay, so after this process is done, we can make the following observations. So yeah, if we are finished with this process successfully, we should now only have even frequencies. So these even frequencies come in blocks of even values, which are separated by zeros. So for example, in this case, we have 3 blocks, which are given by these, and these are separated by like ranges where there are no coordinates with that value. And we can sort of consider each block separately now and sort of add up the answers, so the number of pairs we can make in each block. And since each of these frequencies are even, we can always pair them up into the same pairs, right? Like we can always make pairs of the same coordinate since each frequency is even. So this tells us that the pair odd that we computed earlier is actually a lower bound for the number of adjacent pairs we need because we can fill the rest with same pairs. So now we need to find what's the minimum number of same pairs, or in other words, what's the maximum number of adjacent pairs we can make. So now to answer this question, we can make the following observation. So to find the minimum number of same pairs, we could do the following greedy strategy. Essentially, we'll go from left to right and we'll consider pairs of adjacent frequencies. So let's say we have frequent coordinate I and coordinate I plus 1. If there are more points with coordinate I, so the less frequency is higher, we can fill them up with same pairs and remove those pairs until those two frequencies are equal. And then afterwards, we can pair off every coordinate on the left, so coordinates I with coordinate I plus 1. And this ensures that we create the maximum number of adjacent pairs as possible. And then once we create these pairs, we can remove them from I plus 1, and then we can process the next set. We can process I coordinates I plus 1 and I plus 2, and then so on. And then we can store our answer, which is the minimum number of same pairs that we created. So we can let pair same be the sum of these same pairs that we created over all the blocks. And now we can see that the maximum number of adjacent pairs is n over 2 minus the pair same. This is because pair same is like a lower bound, like the minimum number of like same pairs that we need to create. It's not possible to make less same pairs than this value. Additionally, we can also observe that if we have 2 adjacent pairs, then we can convert them into 2 same pairs. And so this tells us that the set of possible A is this range where we have the minimum number of adjacent pairs is pair odd, the maximum number is n over 2 minus pair same, and every multiple of 2 in between that range is an achievable value of A. And so this leads us to our solution idea. Essentially, we can simulate the following process for both x coordinates and y coordinates, and this gives us the set of valid like number of adjacent pairs. So this tells us which number of adjacent pairs and which number of same pairs are possible for both x and y coordinates. And then we can just determine if there's a match. More specifically, we can determine if there's values a and b such that they add up to n plus 2. So there's a total of n plus 2 pairs. And it's possible to make a adjacent pairs of x coordinates and b adjacent pairs of y coordinates. In this way, we can match adjacent pairs of x coordinates to same pairs of y coordinates and vice versa. So now let's see how we can implement the solution in Python. So first I have code here which reads in the input for all test cases. And the first thing we'll do is we'll define a function which will return all the possible values for the number of adjacent pairs we can make given a list of coordinates. And we can first sort the list of coordinates, and now we need to create a frequency array. So what we'll do is create an array which will store all the unique coordinates as well as their corresponding frequencies. And we can do this by going through the coordinates which are sorted in order. And if the current coordinate is the same as the previous, we can update the most recent frequency. Otherwise, we can add this like new unique coordinate and set it to a default frequency of 1. And once we have that, we can define our answer array, which is like whether or not it's possible to achieve a certain amount of adjacent pairs. And we'll just let m be the number of unique chords we have. And now here comes the process where we simulate our two greedy strategies to find pair odd and pair same. So yeah, initially we have pair odd and pair same over here, and some of these other variables. So open odd essentially means whether or not the previous frequency was odd. So if the previous frequency was odd, we need to subtract 1 from the current previous frequency in order to account for that and update like the pair odd. We add 1 to the pair odd since we're removing that pair. And previous frequency is implementing the second greedy strategy, which is essentially the number of points on the uh on the frequency to the left. And we're doing this so we can match up as many of the frequencies as possible to create the maximum number of adjacent pairs. And whatever's left over is what's going to be like pair same, the minimum number of same pairs we have. So to do this strategy, we can first loop through all of the coordinates in order. And to do like the strategy of removing odd pairs, we first check if the frequency is odd. If it is, we have to remove that pair, and we set open odd to be true so that the next time we go to the next frequency, we'll have to subtract 1 from that frequency as well. And then for the second strategy, we can check whether the previous frequency is greater. If it is greater, we need we need a certain number of same pairs in order to make up the difference and make it so that they are the same. Right? So we need to add the difference here. And otherwise we can just add up as many pairs like as we want, right? So we'll just pair up the previous frequency and make that number of adjacent pairs. And so the new frequency of the current coordinate I is going to be that frequency minus the number of pairs we made in this turn. And yeah, now we can update like the previous coordinate to the coordinate we just did. So that's the end of one iteration. Now, of course, we have to check like whether or not we have gone like we're part of the same block or we've gone to a new block, since we'll have to update that as well. So this will check whether we're part of the same block. If we're part of the same block, and of course, if we have an open odd, that we need to update. So we need to subtract 1 from the current frequency and add 1 to the number of pairs we make for pair odd. And now like our current thing is we no longer need to subtract, so we set this to false. But otherwise, if this means now that we're creating a new block. So if we're creating a new block, but the previous frequency was odd, then there's nowhere for that frequency to be paired with. So we just return an array of false, saying that it's like not possible. And then we also need to account for whatever is left over from like the rightmost coordinate of the previous block. And we need to add that to pair same since it's not possible to adjacent pair that, since we're now moving to a different block, which is separated by 0, or coordinates which don't appear in our list. And so we essentially add the remainder to pair same. And then now that we have that, essentially, and now we can do that same at the end. Essentially, at the end, we're adding the remainder of like the leftover frequency that we have, and we're adding it to pair same. And this now that we've got pair odd and pair same, we can essentially loop through this range of pair odd to n divided by 2 minus pair same in increments of 2, and we can set that to be equal to true. And this will, given a list of coordinates, determine the set of possible like numbers of adjacent pairs we can make with that coordinates. And using this, we can solve the problem, right? So now we can find the possibilities for the x coordinates and the y coordinates. And to see if there's overlap, we're going to loop through the array and check if there's two elements such that both of those are possible for x and y coordinates and they add up to n divided by 2. If that's true, we'll set OK to true, and then we'll print yes, and otherwise we'll print no. So now we can test our code on the sample test case in USACO. So we can run our code. And pasting the sample test case, and we see that it gets the correct answer on the sample test case. And this solution will get full credit for this problem. And thanks for watching. I hope you guys learned something from this video.